All right. So I think we're at the top of the hour and we can get started. So thanks everyone for joining today's October month Community Sync. If you're new here, Community Sync allows community users to meet, interact, and exchange ideas on Apache Hudi and how is it implemented in various organizations for their data lake house or data lake architecture. So today we have very interesting presentation from Shopee's engineering team. And during this presentation, our speaker, whom I will introduce in a couple of minutes, they will present their approach to optimizing real-time queries on massive data sets, large-scale data sets, while reducing the data ingestion cost with Apache Hudi. So before we go into the actual presentation, we'll be going over the community stats and updates for this month. Since the last month, we have chatted a little bit more. Then we will start our session and end with kind of a quick Q&A. This would be pretty much a asynchronous Q&A rather than more of a synchronous thing. But we are live on LinkedIn, so feel free to post your questions in the chat as well, and we can take it from there. So in terms of the community stats, in the last month, we have had around 84 PRs. And, that means a lot has been brewing on the Hudi project side, which is really great. We have had 25 developers who have contributed to these PRs. We also closed around 31 issues around this period. And there are also new PRs being worked on. One of the highlights is that we are talking about the Hudi 1.0 release now. That is getting pretty stable. And that means that we are very close to releasing it. Which means that we can think about a lot of the interesting updates that we have been talking about in the past couple of months, and also for people who have had the opportunity to test out the beta versions. Thank you so much for the feedback and sharing all around Hudi 1.0. So in terms of the community growth numbers, we have over 4,500 users on Slack today. Slack is a great place for Hudi users to bring up any discussions, issues while implementing Hudi, knowledge guides. And there are PMCs to chat one-on-one. So I'll share the link in the next slide for you to join. There is also QR code if you want to just scan that and just quickly join the Slack channel. On the GitHub side, we have around 5,400 stars. So really good momentum over there as well. And we see that increasing over time. And here's the kind of the QR code if you want to just scan it and join our Slack channel for be part of the community. And if you haven't already given us a follow on LinkedIn and other social medias, please do so. We post all the latest updates that are happening in the project, breakdowns of the important concepts, and it's kind of an easy way to digest things around Apache Hudi. So with that, let's welcome our speaker. We have Bradley Pitt from Shopee's engineering team who is joining us today. Let me add Bradley to the stage quickly. Hey, Bradley. I think you are muted, but I'll let you unmute you. Yeah.
Okay.
All right. Yeah, I think we are live with Bradley. So Bradley is the expert engineer at Shopee's engineering team. He has been leading the data architecture strategy for Shopee for quite some time, and also has been a very involved member in all the open source projects in the big data space like Presto, Spark, starting from the Hadoop era, and now with Apache Hudi. So with that, Bradley, I'll add your slides to the stage and you are good to go.
Okay, thank you. Hello, friends in the live stream. Thank you for the Dipankar and Ethan for the invitation, giving me the opportunity to share my work experience at Shopee with all of you. Today, I will be presenting a 12 titles innovative solution for large-scale real-time analytics using Apache Hudi. When we ask GPT what a real-time data warehouse is, it tells us about two key characteristics. To first, processing and updating data with minimal latencies. And second, enable timely insight and decision making. In programmer terms, this means ensuring the data fairness and low latencies queries. One common issue in the industry is the repeating copying of the data across multiple systems. As illustrated on the right, we can we can see on the right. Data from the database is copied to the ClickHouse ES and hooded, meaning the same data exists in the multiple systems. MyCircle and Hoodie store the data permanently, while the Elastic and ClickHouse, due to the high cost, only store data for 1 year. The cost of redundant data storage is quite high, and the growth rates of the business and the data are not always aligned. If the user growth 30%, our data might double, and the Shopee more than 15 grow each year, which continually increase service costs and pose significant challenge for us. We have been contemplating whether we can use a single data to serve multiple business scenarios. This approach should prevent redundant data copying, reduce storage costs, address data inconsistent issues caused by multiple data copies. It might also simplify the system architectures and low maintenance costs. With this in mind, we first analyze the types of queries of business needs. The queries can be broadly categorized into two types. The point queries, targeting the records or a small group of records, usually based on the primary keys or unique key. For example, we provide a user key to query a user table. Compressed query involved multiple tables, aggregation, sorting, or subqueries. Given Hoodie next, we evaluate the data copy situation across different systems. MyCircle have high storage costs and excellent query performance. Elasticsearch and ClickHouse have high storage costs and moderate query performance. Hoodie, on the other side, have the lowest storage costs but the poorest query performance. Given the Hoodie advantage in low-cost storage for massive data, we decided to build a high-performance query service on the top of Hoodie to support various business query scenarios. We chose the Hoodie to build the high-performance systems, query systems. Let's take a look at how Hoodie supports multiple business query scenarios. First, let me explain the meaning modes of the three colors in the diagrams. The yellow represents business components. The blue represents big data components. The green represents the newly added components. In our architectures, the yellow to client-wise queries MyCircles, and the AD part queries ES or ClickHouse. Meanwhile, behavioral log, and the MyCircle data are copied into Hoodie. These are common architecture patterns in many company. To organize queries, we introduce a new query engine, the online engine. We can see the online engine here. Okay. Some requests from the to-C queries and admin portals redirected to the online engines. For example, requests from the to-C service to Korea bills older than 1 year are redirected to the online engines. Of course, less than 1 year is still it still query my circles. We just redirected the request more than 1 year. To cooperate the online engine, we build index storage in external directories. Average the ordered nature of the data by introducing merge-based compaction and merge-based log compaction. I will explain it in the next slides. Okay. After launching the Hudi-based queries service, my circle only retains data from the past year. Elasticsearch and ClickHouse will delete the raw data and keep only secondary index data. All queries for raw data will redirect it to Hudi. Here. We can see the diagram. In this way, we have optimized the data storage and query processes, reduced the storage cost, and simplified the system architecture. Currently, Hudi cannot fully meet our business need, especially when it comes to low latency query service. The business demands that the data latency be within 10 milliseconds, meaning the delay from the data generation to be correlable should not exceed 10 milliseconds. The specific query latency requirements as follows. We can see it in the slides. Point queries should respond in less than 5 seconds. Okay. Paginated queries should respond less than 7 seconds. And the glue aggregation queries need to perform at near overlap levels. While the business have aligned demands for the query performance, it also offers some lenient conditions. For example, the sorting fields for paginated queries can be fixed. We can see the examples. Okay, we can see the examples. Typically sorted by the time. It means order by time. Glue aggregation queries can be grouped by primary keys dimensions. Primary key dimension. We can see the examples. Okay. Regarding the computation cost requirements, we cannot significantly increase computational costs because our existing computational resources are insufficient to support large-scale Hudi table integration. To meet these requirements, we need to optimize Hudi to ensure that we provide high-performance query service while maintaining low cost. The most efficient way to improve query performance is anti-index. Therefore, we have introduced a set of query index in Hudi similar to those in ClickHouse to accelerate Hudi's query performance. The first, let me talk about the index designs in the Hudi, in the ClickHouse. ClickHouse index design is a typically overlapper designs, similar to designs found in other overlap systems like Starloss, Apache Hudi. Okay. ClickHouse uses a script index for secondary indexing, but script index can suffer significant performance degradations when faced with high recall rates. For example, we can look at the slide. We have an example for that. Imagine we have a user table where primary key is user ID, and there is a min-max secondary index on the order ID column. Even if order ID is globally unique, query data using order ID can still result in scanning many irrelevant data blocks. Because we can see the slides, the order ID is a streaming 1 2 3 4 5 streaming. Okay, my fault within, because this order ID my fault within the range of multi data block, even though it is a global unit. Okay. Well, now that we understand ClickHouse secondary index, okay, let's look at the designs for the Hudi, Shopee Hudi. We use a sparse index for the primary key and a combination of the hash index and sparse index for the secondary index. Okay, it means the primary keys use the same as the ClickHouse, and the secondary index use the hash index and sparse index. The sparse index, okay, and sparse index. Okay. This design aims to enhance query performance while avoiding the performance issues caused by the high recall rates. Just the above example is praised. With these index structures, we can meet the business requirements for the high performance queries without significant increased computational costs. The overview of Hudi index. The delta commit and the compaction mentioned above in the diagram are the main computational components in the Hudi Flink or Spark job topology. Okay, the delta commit and compaction. Okay, we can see it. Let's first take a look at the primary modification in the delta commit. Okay, we can see the red diagram. Okay, the first one, sorting the incremental data by primary key to generate the primary key index and secondary index. Store the index in an index file. Append the data block to the log block, especially to the log index file 1. Next, Let's examine the primary modification in the compaction and the next diagram in the red diagram. Okay. Shop the input records by primary key when generate a new base file. Generate an index file specifically in base index file 2. Base index file 2. With this modification, Shopee Hudi ensure efficient data query through its index designs, significantly enhanced overall query performance. Okay. At this top, we mainly talk about the designs, what we change in Hooded. Okay. To generate a sparse primary key index, we sort the records by primary key when writing them into the log blocks during the delta commit. This means the records in the log blocks are ordered. Because the records in the log blocks are ordered, using merge sort algorithms yield the best performance when generating the base file. Therefore, we introduce a new compaction method, compaction with merge sort. The implementation details mainly include two key points. Construct a min hint based on the log blocks input string and the base file input string. We can see the diagram. Okay. While iterating through the records in the min hint, merge identical records according to the record merge strategy. Finally, by traveling the min hint, we obtain records ordered by primary key, and these records are written into a new base file, thus completing the compaction process. We introduce a compaction with merge sort to ensure the data is ordered by primary key. But do this introduce any other issues? Let's first take a look at the existing compaction method in the community, map-based compaction. In this process, compaction reads the base file and lost files of a file group and write the records into the map that can spill over to a file. We can see the diagram. Okay. When records with the same primary keys are encountered, they are merged. Then, by iterating through this map, data is written into a new base file, completing the compaction process. In the contrast, our compaction with merge sort method not only ensure data order, but also improve performance. It means we don't introduce any other issues. We achieving data orders and also improve performance. We can see the red diagram. Okay. The key to these performance improvements lies in avoiding the disk overhangs associated with the map spilling to a file when it overflows memory. Especially, compaction with merge sort is achieving through the following steps. It iterating the min him, it will not have the overflow memory then that have overflow the memory to this overhand. Okay. Okay. When Hudi computation performance is already impressive, we further reduce the resource consumptions when computation resources are limited. Because our company computation resources are limited, we found that to ensure the smooth operation of compaction tasks, Flink need to allocate substantial resistance resource. However, during actual operations, this resource can be idle at times, leading to resource wastage. Given that compaction is essentially a batch processing task, allocating resistant resource to learn batch processing is clearly an inefficient use of resource. Through our research, we discovered that Hudi already offers an option for async compaction to address these issues, especially with the async compaction. Flink, while disable the learning of compaction, only generates a compaction plan. Then the sparse job is periodically triggered to execute the compaction task. By adopting this approach, we can efficiently avoid the idle states of resistant resource. Thereby, we reducing the resource wastage and achieving more efficient resource utilization. Let's summarize Hudi performance in terms of resource consumption and corollary efficiency. Okay. Taking MOR tables with daily incremental loads of 115 GB eval log as examples. Let me compare the performance of the community Hudi and the Shopee Hudi. When it comes to points queries and paginated queries, Shopee Hudi significantly outperforms community Hudi, especially our point queries and paginated query times can be reached 70 seconds and 20 seconds respectively, which is a notable improvement over the community Hudi. More important, despite the substantial boost in the query performance, our computational costs have not increased significantly. To demonstrate that Shopee Hudi optimized query performance while maintaining low resource consumption, showcasing its balance advantage between performance and cost. And we can see Shopee Hudi generate one primary key index and two secondary index. Okay, we can see the sparse cost is more than community Hudi because our ending the index because we ending generating index cost. Okay, but our query time is high performance than the community Hudi. Okay. New issues. During our testing, we discovered the query types are inconsistencies. Sometimes stabilizing around 3 seconds, but occasionally increasing to 10 seconds. After a thorough investigation, we found that this was due to a significant increasing in the log block fragments within the log files. We can see the slides. We can find the log block fragments, which led to increased this I/O performance degradation. Especially multi-log blocks within in the log files. For example, from the log block 2 and the log block 8 form the fragments. When queries incremental loss, each log block needs to be checked, which significantly reduce query performance. To address these issues, we can increase the compaction schedule frequencies, can adjust the log block fragmentation issues, but each compaction requires looking and merging all data, which is computational expensive. To address these issues, we introduce a lightweight log compaction mechanisms designed to merge log block fragments. Take a look at the diagram below. Those log compaction, we can merge multi-log block fragments, such as log block 2 and log block 8, into a single new log block 9. In this way, query process only need to access log block 1 and log block 9, greatly reducing the numbers of log blocks that need to be accessed. This reduces the access to 7 log blocks, significantly improve the query performance. In the single file group, we already reduced the 7 log blocks. If there was 10 file group, there will be 70 log blocks. We can reduce the 70 log blocks, reduce the access to 70 log blocks in 10 file group. In this way, we improving query performance. Finally, let's summarize Hudi performance in terms of resource consumptions and query exceptions. When it comes to point queries and paginative queries, our performance has further improved, reaching 5 seconds and 7 seconds respectively. This significantly enhances query efficiencies. What even more is that these performance gains have not led to a significant increase in our computational costs. This demonstrates that Hudi optimizes query performance while still maintaining a low resource consumption, achieving a great balance between performance and cost. After launching the systems, we successfully onboard 5 business units. By offloading some sub-queries requests to the hooded, these units can confidently delete redemption. This unit can confidently delete redundant data copies. As shown in the diagram, for these 3 business units, the data team has already held business cut down over 200 servers, significantly reducing the cost. Okay. The diagram only shows 3 business. Actually, we have 5 business. Okay, we actually help business cut down more than 200 servers. Look ahead, we will continue to enhance our multi-dimensional analysis capabilities. These include glue aggregation by primary key dimensions, glue aggregation by arbitrary dimensions, and the jump operation between tables. Okay, a special thanks to Dipankar and Ethan for their help, and we will contribute this feature to community hooded insurance, and as soon as possible. Okay. Thank you, everyone. Thank you, the friends in the live stream.
Thank you so much, Bradley. Yeah, this was really insightful, and I'm so glad to see that you have taken like the community version of Hoodie, which already was giving you a better performance, more consistency guarantees, but also like how you have like built something using this, and that you're planning to open source to the community as well. So really appreciate taking the time, and also it's like I wanted to take the time to thank you. It's midnight in China, so I really appreciate taking the time as well to present this. I think our audience will be super excited to know that you are thinking of the open source community contributions as well. So really appreciate that. We do have a lot of questions, but I will let you take them offline for our viewers. This time we are going to do a little bit of asynchronous question and answers. So I'll let Bradley leave today, but I'll get back with the questions and answer from him, and also the slides and the recording will be available for the community users as well. So thank you so much, Bradley, once again for joining today, and sharing your presentation and sharing all that you have been doing at Shopee.
Thank
All right,
you.
bye everyone. Thank you.